Okay, let's have a look at what we might do with a conventional boiler house where standard equipment is fitted and the owners want to have an upgrade. In that situation, you might find that a standard boiler might be in place, something like this, standard flow and return connected to whatever. Typically very difficult to follow, extremely awkward to try to improve efficiency on system efficiency, whatever about boiler efficiency. But if you introduce an energy zone manifold, you see that from the very start, by removing the existing pipework and installing an energy zone manifold and connecting to the existing zones or including new zones as might be piped back to the renovation, you have a situation already where there's a logic to the system. The flow leaves the boiler and travels in to the top chamber in the unit. It will, on its own pump duty, travel back around and go back to the boiler. But in the meantime, it will have offered itself to the zone flows for the different zones. Like here we have a twin pump for zone 1, zone 2, zone 3. Energy zone manifolds can be made for specific jobs. For example, if you had maybe 2-inch or 50mm flow and return for zone 1 and maybe the same for zone 2, you might have, say, inch or 25mm for zone 3, different zone 4, back up to 2-inch for zone 5, and maybe a hot water zone. So the manifold can be made to suit the job. The zones can be located wherever, and in fact flows can be kept together and returns kept together as groups, instead of having in this situation in sequence flow, return, flow, return, flow, return. So in each of these situations, the pump draws water from the manifold, which acts as a neutral point in the system, and sends it out around the system, and then the return comes back in and is captured in a lower chamber, which collects all the return water and makes it available for more efficient equipment, as you'll see. So on the side of the unit, of this particular unit, and they can be made to suit any given job, there are a number of ports. L1, top flow port, where heat would enter into the unit. L2, which is a system bypass, where having travelled right across over a plate within the unit, it can travel back to the boiler. And port L3 is where colder return water could be collected. So again, expansion equipment, whether it's sealed or open systems, can be manufactured into the unit. In this situation, we're showing a pressurization unit located beneath the manifold, and which has access to all of the pressure within the system, because there are no obstructions within the manifold that could in any way hinder the expanding water as system water heats, as the contents heat. Same applies on the other side. You also can have whatever ports you require. For example, here we have an optional flow port, R1 at the top. R2 is again connected into the central chamber of the manifold, and R3, on the arm being right hand side, is connected into the lower zone return chamber. This is a special unit, specially made, for example, for this particular job. What's notable here is that all water, whether it comes from this side or from the other side, in this side it travels through an internal pipe and turns back on itself and travels back to this point, and also if it flows from the other side, it travels outside that same pipe. So all water and all air in the water will catch in a trap, an air trap that's set here, and this is where air would be released from the system from the very start and right through every time water passes. It's always important with any equipment, particularly with the NRG zone, to have it so that the pipe connecting the automatic air vent should be directed away from directly above the manifold, in case the vent ever leaks or there's ever any problem, so any leaking water will not fall onto pumps or anything that might cause some damage. So always keep the air vent to one side just in case. In this situation again, you see we have some sensor points. We have one here on the flow, and you'll see there's a number as well on the other side, sensing the flow temperature coming in and also the return temperature going back. Again, they can be located into whatever manifold is decided is best to suit the purposes you require. In this situation, so we have a boiler and multiple zones. If, for example, we wanted to add a bank of condensing boilers, I'll show you how you might go about that. But just again, here we've located temperature gauges, so you can see flow boiler flow is coming in. The end of the term of the manifold top chamber, so you can determine that there is heat available for all the zones if this remains hot. If this is cold, obviously the primary pump is not delivering enough water to satisfy all the zones, and so this will indicate that in fact this pump is performing properly. Without tools, you can see straight off that the system is doing what it should do. This sensor here will determine if the water might be, for example, too hot to head back to heat pumps or whatever. But sensors can be located literally anywhere. So if we introduce gas boilers, as in this situation, you might have a bank of gas boilers with a common flow, condensate drain going to the outside, and then you'll see that the flow delivers water into the top chamber, and this pump here serves a particular purpose. It's not necessary to have this pump if the boiler pump is capable of delivering all the flow water necessary for all the zones passing through. But if you have boilers like these, where for example each boiler contains two separate boilers, so this pump might be handling half of this boiler's load, this pump the other half. So in other words, we have 3 casings, but actually there are 6 combustion chambers inside. One of those pumps might not be capable of delivering all of the volume necessary, but it would be capable of delivering the heat for a given time. So for that reason, the pump will deliver the heat into the flow, the heat energy. The heat will come up to here, and it's this shunt pump that causes the circulation to pass all of the zones. So you can have a minor amount of heat energy and yet have constant flow with using this shunt example. The non-return valve located here just shows that makes sure that water will always flow that direction. So if heat arrives from the boiler here, it's picked up by the flow of water passing through the non-return valve, around the flow chamber, back into the return chamber, and back around again. If any zone is using heat, the coldest water is collected, and that's what's offered back to the condensing boilers, making sure the condensing boilers always have the absolute best opportunity to condense and therefore increase their efficiencies. So if you look at the boiler room now, you can see that although we've put quite a lot of extra work in there, it really is not in any way complicated to understand, and certainly is a very easy installation. So we still remain with the old boiler, but let's say the new boilers have their desired effect and the building running costs start to drop. They will drop because condensing boilers are better, they're modular boilers, they will cause serious efficiency improvement. So now we can consider removing maybe the old boiler and instead to put in more efficient equipment, for example heat pumps. In that situation, you would simply put your heat collectors on the outside. In this example we're showing air to water heat pumps. The refrigerant gas comes into the heat exchangers or condensers. The condensers take that heat and convert it into flowing hot water. Each of those exchangers has a built-in pump which will circulate the water into the flow and through the unit, return back, pick up more heat. With this example, you can take the flow water and you can direct it straight into the flow chamber and therefore feed all of the zones if you wish. And if the water temperature is not hot enough with the heat pumps, but you still want to use the heat pumps, you can instead use a diverter valve to divert the flow water down and across the bypass chamber, where it will be picked up by the gas boiler and taken down in through the gas boiler, reheated to a higher temperature and sent in. So therefore the heat pump can supplement the gas boilers. So the heat pumps are not turned off just because the gas boilers are working at higher temperature, because if there's water is cold enough to justify the heat pumps being used, then this sensor will tell a building management panel or whatever panel is controlling the system that the heat pumps can still run. If it gets too hot for the heat pumps and there's no point running the system, then a control would turn off the heat pumps and let the gas boilers continue. In the normal situation, the heat pumps would work for a huge amount of the time, and therefore the running costs and efficiencies of the system will be greatly maximised. So if you look at the heat pumps, each of the heat pumps again will have, in this particular model, will have two heat pumps inside, two heat exchangers, and each one with its own control. So as the heat pumps start to deliver heat out, it will start to collect inside and be delivered up through a non-return valve and around through the 3-port valve, either be fed directly or to preheat the gas boilers. This particular valve scenario is not necessary on every job, but it's just an example of what can be done if you want to take full advantage of heat pumps operating with gas boilers or with any boiler, even when the other boiler is up to temperature, because as you say, you can preheat the return. So now you see that with the heat pumps in place and with the gas boilers in place, we've got an extremely neat, very efficient, extremely user-friendly boiler house. If, for example, we want to add some hot water, a hot water circuit could put in whatever calorifer is necessary. In this example, we're showing just a nominal size, maybe 300 or 400 litre. You could take two supplies into two separate coils in the heat calorifier. For example, you could have low temperature feeding through this twin pump and down, and feeding into the coil, heating the coldest water with the heat pumps, and therefore providing maybe 40 or 50 degrees at a very efficient low running cost. And then you could have the gas boilers come in, where this valve would open and the pump would draw the gas boiler water directly out and heat the water as it arrives at the top of the tank. So in other words, you can have the benefits of extremely efficient heat pump heating on the coldest water at the bottom of the tank, and the gas boilers bringing it up to full temperature. In this situation, you really have the best of both worlds. So with the domestic hot water scenario, you can just bring it up to whatever temperature, low temperature, directly with the heat pumps only, or you could just use the gas boilers on their own. So now you can see that we've got heat pumps, condensing gas boilers, all modularly can put together, all of the zones separated, a little bit of thought put into how the heat pump will take most advantage of the efficiencies, and the shunt pump offering a very simple solution to overcoming the problem with modular boilers having smaller pumps that might not satisfy all of the load. Hope you enjoy this and hope we can be more helpful with more videos in the future. As always, energy awareness, bringing you information on Energy Zone.